So for the rest of this lecture, we're going to be discussing the Gaussian. But however, before we discuss the Gaussian, let me introduce a concept which I'm going to call the uncertainty of an observable. So suppose we have an observable O, then we can define the uncertainty as, not use the caret. So this will be the difference between the observable and its average squared and the average of that square root. So this is basically the mean deviation that we know from the probability theory. So for position, the uncertainty in the position will be given by So if we look at the square of the uncertainty, then there's a very easy, nice way of expressing it. So we can express the square in the average. It's going to give me x squared minus 2x times the average of x plus the average squared, and the whole thing is averaged. So now the average commutes with, well, the second term is going to be 2 times x, because this is just a constant. So this comes out of the average. And then the last term is just the average squared. The average of the squared minus square of the average. So this is a nice expression that one can derive of the square of the uncertainty. So similarly, the uncertainty in the momentum is going to be given by this thing. So one can compute the uncertainty for a wave function which has the form of a Gaussian. So we can take a wave function at some given time, and it's going to be x squared by, say, 2 sigma squared divided by this. And now if I compute what the uncertainty is in the position of this guy, then we'll find that it's going to be given by sigma over square root of 2. And similarly, if we compute the uncertainty in the momentum of the Gaussian, then it's given by h bar divided by square root of 2 sigma. And the product of these two things, delta x and delta p, is going to be then h bar by 2. Now, it's a theorem in quantum mechanics that for any wave function, if you take the product of x and p, the uncertainty in the position of the momentum, it's going to be either equal to or greater than h bar over t, 2. And so this inequality is saturated only for the Gaussian wave function. That's a theorem that we may or may not prove at a future date. So we already saw like what this kind of means. It means that if I take the Fourier transform of the Gaussian, of course the Gaussian looks something like this, and the Fourier transform of the Gaussian will also be a Gaussian. And then, the spread delta x and the spread delta p, the product of that remains a constant. So that if my Gaussian is in position space is very tight, it's going to be very broad in momentum space and vice versa. So next, we're going to discuss what the evolution of a Gaussian wave packet is going to be. And I'm going to suppress a lot of the detail, and I'm going to give you the story. The evolution of the Gaussian wave packet. Because this is important, because we expect a realistic particle to be described by a wave packet rather than a plane wave, because a real life particle is going to have some form of localization. So I'm not going to prove it here, but the Gaussian wave function of a particle which has some average momentum, like expectation of p, is given by the usual wave function, the Gaussian, times a phase factor and this is kind of easily motivated, because you saw that if you had a particle whose momentum was p, you had a momentum dependent phase factor which was e to the power I px over h bar. And here what we're saying is that if the Gaussian has an average momentum of expectation value of p, then it is accompanied by this phase factor. So now the question is, how do we predict the future of this wave function? Now we are assuming that our particle is a free particle. So then the general formula is that the wave function of a free particle at time t is given by our time evolution operator with these arguments applied to the wave function at an earlier time and integrated over all of space. So, and we saw that u of xt x prime of 0 is given by m times 2 pi I h bar t under a square root e to the power I m x minus x prime squared divided by 2h bar t. So now if I do this integral, then this is essentially a Gaussian integral, and you can use the extension of the Gaussian integral, which I'm just going to give you now without proof, but it's very easy to prove. If you know the Gaussian integral, it's just a way to complete the square. So this is the Gaussian factor, but suppose that we have another factor which is linear, then this is given by pi over alpha square root e to the power beta squared by 4 alpha. You can prove this by using the Gaussian integral. So we can use this to do this integration now, and if I do this integration, the final result is going to be psi at a later time t is given by 1 over sigma square root of pi, the whole thing square rooted, sigma divided by some time dependent factor which is called alpha, not this alpha, this is a different alpha. And then we have e to the power, we have a Gaussian factor, a complicated looking Gaussian factor. We have an x dependence minus expectation value of p over m times t, and this whole thing is squared and then divided by 2 alpha of t, where this is the same alpha as here, and then this is the Gaussian factor, and then we have a phase factor which is I by h bar of p x minus pt by 2m. Okay? And where alpha of t is given by sigma squared plus I h bar t over m. So this is a complicated looking expression. So let's discuss parts of it. So there is a Gaussian factor over here, and that looks like, what does it look like? The Gaussian factor looks like e to the power minus x naught squared divided by 2 alpha squared of t. I forgot the squared here. And so what is x naught? X naught is the mean position of the Gaussian, because the Gaussian doesn't have to be, this doesn't have to be 0. It can have some other value, x0. And that is basically what this thing is. So here we see that, this is the position, and this is a time-dependent position, the mean. And therefore, there is a velocity there. So the time-dependent mean position is this thing. And therefore, we see a group velocity. So there's a group velocity here. The group velocity is p over m. So this is the first observation. The second observation is that if I now take my wave function and square it, we find the probability density. And in the probability density, this momentum-dependent phase factor, it's a time-dependent, position-dependent phase factor, that goes away, because this is just a phase. And my probability density is going to be given by sigma by alpha squared. This is a time-dependent object, square root of pi. So the probability density itself is a Gaussian. All right, and now what we can do is that we can compute what the expectation value is as a function of time. So we can use this wave function and compute what the expectation value is. And that can be computed to show it's sigma by 2 square root of 1 plus h bar squared t squared by sigma to the power 4 m squared. So we see that the spread of the wave function, the spread of the probability, depends on time. Where to plot this? So I have on the x-axis some time coordinate. So here on the x-axis, I'm plotting a rescale time coordinate. And on the y-axis, I'm plotting a rescaled delta x in terms of sigma. And then at time 0, it's 1, and then it just increases like that. And so we see that as time progresses, the uncertainty in the Gaussian wave packet increases. So what this means is that, if the Gaussian wave packet, looked very sort of localized, so we knew the particle was somewhere here, after some time, it spread out, in a way that, the area under the curve is the same, is 1. So now we know, less and less where the particle is.